Yeah, we have studied the first two sections in chapter 4, algorithm, and today we will finish up the chapter 4. Section 4.3 start with the analysis of algorithms, and we will finish up the whole chapter 4, and I gave you problems to solve in chapter 4 for you. Okay. There are examples of useless programs. Okay. Those are the ones that that may be a correct algorithm, but if it requires the time needed to learn the program is too big, or the space needed to hold the data is too big, then actually that algorithm is not in use. Okay. Let's start with an example. Let X be a set of n elements. Of some elements are labeled red and some labeled black. Then find the number of subsets of X that contain at least one red item. Okay, on this problem, since a set that has n element has how many subsets? It should have 2 to the n number of subsets. So program would require at least 2 to the n units of time to execute. Let's consider how big this number is when the n goes big. Okay, what if n is very big, then how this number 2 to the n moves. The time needed to execute an algorithm is a function of the input. Okay, we use parameters that characterize the size of the input. Okay, as n goes to 3, 6, 9, 12, 50, 100,000, and 10 to the 6. As you see here, 2 to the n goes bigger and bigger and bigger, and is far bigger than that you could imagine. This is even you consider 1 as 1 second. 2 to the n is if n is 10 to the 6, then it will take this many years to execute. The cases. So if for certain functions like this, if n is big, then the cases are too many to be considered by even the computers, high-speed computers. So the input is a set containing an element. Then we tell the size of the input is n. Best case time is we can ask for the minimum time needed to execute the algorithm among all input of size n. Then this time is the best case time for input of size n. If the minimum time needed, then we call this time is the best case time for the given input. Worst case time is if it takes the maximum time to execute the algorithm for a given input of size n, then we call that the worst case time for the given input. Average, another important case is the average case time, that the average time needed to execute the algorithm for the given input of size n. Here is an example, 3.1. Reasonable definition of the size of input for algorithm 1.2, which we covered in section 4.1, that find the largest value in a finite sequence is the number of elements in the input sequence. The reasonable definition of execute time is the number of iterations of the while loop. With this definition, for algorithm 1.2 for input of size n, the loop is always executed n-1 time. We have n numbers, we compare one at a time. So we need the n-1 time of executions. So the worst case and best case and average case times are each n-1 in all cases. That's all we needed in any cases. We have to check those n-1 cases, and that's all we need for any cases. There's no bigger or less to check. In that case, those cases are all same as n-1. Okay, we are in how the best case or worst case time grows as the size of the input increases. Here, how the best case or worst case time grows as the size of the input increase. For example, suppose an algorithm is T of n is equal to 60 times n squared plus 1 for input size of n. Then for large n, the term 60 times n squared is approximately equal to T of n. Okay, this is almost same as this. Let's see. As n grows from 10 to 100,000 and 10,000, and T of n changes like this. And 60 times n squared changes like this. As you see, the difference between these two are not that big as n goes high. We can check those. Copy. In cases, if you execute it, 60 times x squared plus the T of x and just 60 times x squared. Let's compare these. As n goes big, as you see, the difference was 51 here. There was a differences. But as n goes high, the difference is getting smaller, and in percentile wise, it's getting smaller and smaller. If we make this is about 20, range 20, then you will see the difference is getting smaller and smaller. There's not difference between this about 15 digits. There's not difference. So difference is very small. It's less than 0.0000001%. Okay. So when we see this algorithm, then all we need to consider is this largest term. That's all it counts. With those ideas in your mind, we define the terminology of Pico notations. Let f and g be functions of domain n is equal to a set of natural numbers, and we call f of x, function f of x is big O of g of n in this notation, which means f of n is of order at most g of n. If and only if there exists a positive constant C1 such that absolute value of Fn is less than or equal to this C1 times absolute value of G of n. Okay, so in this case, if we can find this positive constant C1, then we call this F of n is big O of G of n. This is the definition of big O notation. Next one is opposite. It's the upper bound, and next omega notation. stands for the lower bound. F of n is called the omega of g of n, and also we call it f of n is of order at least g of n. If and only if there exists a positive constant C2 such that absolute value of f of n is bigger than or equal to C2 times absolute value of g of n. Then we call, this is opposite, this is lower bound, then we call, this f of n is omega of g of n. If f of n is theta of g of n, if f of n is omega of gn and f of n is the big O of gn and omega of gn, if we can find this constant C1 and C2 for the upper bound and lower bound, then we call this f of n is theta of g of n. And we also read it as f of n is of order g of n. Like that. If we have upper bound and lower bound, then we call this f of n is the theta of g of n. Big O and omega, both we have C1 and C2, then we call f of n is theta of n. Okay. And then we call f of n is of order g of n. The order of increasing is same between f of n and g of n. Okay. This is important terminology that we're going to use it over and over again in this whole textbook. Next definition, 3.2, can be loosely paraphrased as follows. If f of n is big O of gn, f of n is big O of g, this means f is bounded above by g, the function. Function f is bounded above by function g. And also we call g is an asymptotic upper bound for f. G is an upper bound, asymptotic upper bound for f. If f of x is omega of g of n, then we call f is bounded below by g. And we also read it as g is an asymptotic lower bound for f. And g is a lower bound of f, asymptotic lower bound. Okay? And if f is bounded above and bounded below by g, the same function g, then we call g is an asymptotic tight bound for f. Okay, this is loosely paraphrased the definition of those three notations: omega, big O, omega, and theta. Upper bound, lower bound, and tight bound, symptotically. Okay, now let's take a look on the history of big O notations. Big O notation has been used in mathematics for more than a century, and in computer science it is widely used in the analysis of algorithms. Paul Bachmann first introduced big O notation in 1892 in his book, and the use of big O notation in computer science was popularized by Donald Knuth, who also introduced big omega and big theta notations, as we just learned. And you may know this popular computer scientist Donald Knuth, and Donald Knuth was well known for his book, The Art of Computer Programming, and this book was written when he was the age 28. Okay. Example 3.3. Show that this polynomial is equal to theta of n to the fifth. Show it. So what do we have to do? Seaman, what do you have to do? We have to find the upper bound and the lower bound. So we have to show, in order to show this polynomial is theta of n to the fifth, we have to show this polynomial is a big O of n to the fifth and the big omega of n to the fifth. Then it will be done. In order to do that, so let's write down, let's find the upper bound of this. Okay. 3 times n to the fifth plus n to the fourth plus 17 times n squared per 2 is less than or equal to 3 times n to the fifth plus n to the fifth plus 17 times n to the fifth plus 2 to the n fifths for all n bigger than or equal to 1, always. If you add all those, then it's a 23 times n to the fifth. Okay, so this is an upper bound of this, which is a multiple of n to the fifth, where C1 is equal to 23. So if we choose C1 as 23, then by the definition, this polynomial is equal to big O of n to the fifth. Done. Okay? So we found C1, 23, to show this is big O of n to the fifth. Second, we want to find the lower bound of this. If n is bigger than or equal to 1, then this left-hand side is always bigger than right-hand side, because this is always bigger than or equal to 0. Okay? Actually bigger than or equal to 2, 3, 4. Yeah. So this left-hand side is always bigger than or equal to 3 times n to the fifth. So if you choose C2 is equal to 3, then from the definition, this left-hand side is equal to omega of n to the fifth. Since this left-hand side is big O and big omega, so it should be theta of n to the fifth. Done by the definition. So we showed it. Okay. Any questions? 장효주, Chao. 장효주, Miss Chao. And Kim Chan-ho. Okay, is it clear? 그러니까 폴리노미알 주고 폴리노미알이 이제 세타 오브 n to the 어떤 파워인 걸 구하라 그러면 뭐 구하는 건 별로 어렵지 않겠죠? 다 그러니까 어퍼 바운드하고 로어 바운드를 찾아서 상수만 정해주면. Okay, good. Next theorem. Prove that P of n, this polynomial, with the degree k, is always a big theta of n to the k's, where Pn is a polynomial of in n of degree k, where each ai is non-negative. Always. How? Okay. Do the same thing. Let C1 be the sum of all the coefficients. Then clearly P of n is less than or equal to all the summation of n to the times n to the case. So if we choose this one as C1, we always have this upper bound. So C1 can be chosen to show P of n is big O of n to the case. Next, show the omega. So it is left-hand side is omega of n to the case. The left-hand side is always bigger than ak times n to the case. If we choose 이게 if some of these are negatives, negative면은 조금 달라질 수 있는데, if we choose the enough large number constant, ak or ak prime, that makes this inequality valid and choose that AK or AK prime to be C2, then we can always have these inequalities for non-negative integers n. So, since there exists this inequality and constant C2, so we can say P of n is omega of n to the k's. Since P of n is omega, big O of nk and omega of nk, so we can tell P of n is theta of nk by the definition. Clear? In general. That's the way. Okay. We can see this 2n plus 3 times log n is always less than to the 5n. And so we can tell this is big O of n. 2n plus 3 times log n is always less than, also bigger than or equal to 2n. So we can tell this is omega of n. So since it's a big O of n and omega of n, so it is theta of n. Okay. We can check it. We can check it as when n is big enough. When n is big enough. By draw the graphs. We can draw the graph to check whether it is really true. Yeah, P1 is this equation, P2 is this, P3 is this x times log x, and this log x from 1 to 13. This, you can draw the picture after a certain point, after a certain integer. At the earliest, when n is equal to 1 or 2, it could be the difference. But when n is big enough, then you will see clearly which one is upper bound and which one is the lower bound of it. That's the important things. So you can give a starting point when you need it to use to find this C2 or C1 for sufficiently large number n0 to all the way to the or positive integers. That's the way to show a given polynomial or functions is big O, big theta, or big omega. Next example. Show that 3 times n squared plus 8n times log n is a theta of n squared, as you checked. Okay, let's think this log n is a log of 2 log of n base with base 2. Okay, in that, so consider with it, then clearly log n is less than n for all non-negative n. So we have inequalities like 3n squared plus 8n times n, which is 8n squared, so which is 11n squared. So we have this inequality for all n bigger than or equal to 1, which gives us C1, which is 11, and that gives us the left-hand side is big O of n squared. And also 8n, 3 times n squared plus 8n n squared. This, since this is non-negative, it's always this left-hand side is bigger than the right-hand side. So if we choose 3 as C2, then the left-hand side is omega of n squared. Since it is big O and omega, so it's just theta of n squared. That's it. Okay. Siemens. Clear. Next. Summation of I is equal to 1 to n, I times log I is equal to theta of n squared log n. How we can show it? Same. This left-hand side is always less than or equal to n times n log n, which is n squared times log n. So the left, so if we choose C1 is equal to 1, then left-hand side is a big O of n squared log n. And also this can be written as this. So this is less than or equal to I log I, where I is the ceiling of n over 2. This is always left-hand side is bigger than this, which can be written in this way, with inequalities, which can be written in this way. So we have inequality where this left-hand side is bigger than or equal to this right-hand side, which can be, and yeah, this. So with this observation, yeah, the whole thing is bigger than or equal to n squared times ln of n over 8. So if we define C2 as 1 over 8, then we have the left-hand side is omega of n squared times log n. Since this left-hand side is big O and omega, so it is theta of n squared times log n. So we could show this is theta of n squared times log n. Next, more simple. This summation of 1 to n is equal to theta of n squared for all n bigger than or equal to 1. Okay, sum of this. In order to show this, 1 plus 2 plus data n is less than or equal to n plus data n, which is n times n, which is n squared. So we have, if we choose C1 is equal to 1, then we have this left-hand side is big O of n squared. Next, this is equal to n times n plus 1 over 2, which is always bigger than or equal to 1/2 times n squared. So we have these inequalities. So if we choose C2 is 1/2, then we can have the left-hand side is omega of n squared. Since this is big O and omega, so it's a theta of n squared. Done. Okay? Next, this cube, sum of the cube of the integers, positive integers, is equal to theta of n to the fourth. Similarly, if we from here, yeah, since n is bigger than or equal to 1, so each of them is less than or equal to n cube. So how many do we have? We have n over n cubes, so n times n cube is n fourth. So we have an inequality like this. So the left-hand side is big O over n to the fourth. If we choose C1 is equal to 1. Okay, similarly, the left-hand side, we can find the sum of this with the summation formula, which is less than or equal, bigger than or equal to 1/4 times n to the fourth power. If we choose C2 as 1/4, then we have shown that left-hand side is omega over n to the fourth. Since it's big omega, big O and omega, so this left-hand side is theta over n cube, n fourth. That's it. Yeah, we can check. We can check. We can really compute the cube, how it moves, how it changes. If we add it from k for the n, how many? Sum of from k to d, how many? 50. Then we have this number. If we have this 5,550 terms, then size will be this. And we can easily compute all the summations with this simple command, sum of k to the cube from k is equal 1 to 25,550, so whatever. Anyway, yeah, but even before you do that, we know this size has a bound, upper bound of this, and lower bound of that. So we have a tight bound. Next, example 3.9. Prove this. Zeta of n to the cube. Okay, the left-hand side can be written in this way. As you see, this is always less than 2 times n cube, because you can factor it out and add all the thing. Yeah, you can easily make the inequalities, and we know that. So if we choose C1 is equal to 2, then it is big O, and from here, this can be written as this, and since this is non-negative, non-negative, so this inequality holds. So if we choose C2 is equal to 1/3, then we can show the left-hand side is omega of n cube. Since it's a big O and omega, so it's a zeta of n cube. The same thing can be done. You can add all the terms, and you will see it's not growing that fast. Okay, so from here, you will see n to the cube or n to the square, n to the fourth is not growing that fast. But 2 to the n was growing really fast. That's what you found. Okay, so if f of n is big O of gn and gn is big O of hn, then f of n is a big O of hn, like transitivity. Okay. This is true because if this is true, then there exists a constant C1 that satisfies this. And if this is true, then there exists constant C2 that satisfies this, or C3, whatever. If we multiply those two constants, then we have the absolute value of f of x is less than or equal to this, and which is less than or equal to constant multiple of constant times absolute value of h of x. If we define this C1 and C2 as C4, then there exists a positive non-negative constant C4 that satisfies this inequality, which says f of n is a big O of hn, because this is a one constant, okay, non-negative constant. So if fn is big O of gn and gn is a big O of hn, then f of n is big O of hn. So this is an interesting and important fact that we're going to use over and over again. Next definition. If an algorithm requires t of n units of time to terminate in the best case for an input of size n, and the t of n is big O of g of n, then best time required by the algorithm is of order at most g of n. That's what it means. Okay? And if t of n is big O of g of n, then the worst case time required by the algorithm is order at most g of n. And if t of n is equal to big O of g of n, then the average case time required by the algorithm is of order at most g of n. Okay, that's the another paraphrase of the terminologies and concepts that we have covered in Barber. Next, example 3.12. An algorithm needed this unit of time to terminate in the worst case for the input of size n. That we showed in the example 3.3, this is equal to zeta of n to the fifth. So the worst case, time required by the algorithm is zeta of n to the fifth. So it is controllable. Okay, I think that's the end of the section 3.13. Okay, find the zeta notation in terms of n for the number of times the statement x is equal to x plus 1 is executed with this loop. Okay, then first I set to 1 and j learns from 1 to 1. Line 3 is executed one time, and next I is set to 2 and as j learns from 1 to 2. So with while loop, the total number of times in lines executed is like this. So the iterations that we have made is zeta of n cube. So the zeta notation for the number of times the statement x is equal to n plus 1 is executed is zeta of n cube. Actually, yeah, we do see a pseudocode for searching an unordered sequence like this. Given a sequence S1 up to Sn and the value Kn, and value key. This algorithm returns the index of key. If key is not found, the algorithm returns 0. So input is the sequence and key, sequence and n and key, the value that to search for. Then output is the index of key, or if key is not found, then print 0. Then this linear search code will give you the index of key when it is found, and if you don't find it, then it will give us zeros. And that's the one code for searching key, the index of the key. And next one is the matrix multiplication. This algorithm computes the product C of the two matrices of size n by 1 directly from the definition of matrix multiplication. So if you give two matrices and the size of the matrix n, then C, which is the product of two matrices, will turn out with this code. This is the kind of using King Sejong's rule, that the inner product of row and the columns of the matrix A and B to find the Cij, which is ij's index, right? Ij's entry of the matrix C with this. This will give us the matrix, which I showed you in here. Matrix that gives you the product. So if you define a matrix A and B of same size, then C, which is output, will come out with those code. Whenever whatever matrix is of finite size, of same size of two matrices A and B, then you will have the product of the matrix with that code. Okay. And the last table shows the common growth functions. Zeta of 1 is a constant, zeta of n is a linear function, zeta of n square is a quadratic function, and zeta of n to the cube is a cubic, and polynomial of degree k then is it's a upper bound of the polynomial of degree k, and exponential and factorials, and those are the typical the functions g of n that you're gonna use to compare the given function f of n when you find the upper bound and the lower bound. So you compare, consider these type of functions to deal with the problems in here. Okay. Copy. And chapter 4, solutions. Oh, I see. Solutions. Copy this. See in Google Chrome. Here, I have uploaded the solution of the problems in chapter 4 in this web address. So, if you have any question, you go back here, and if you have anything that you don't understand, you can ask questions, and you may try to solve some other problems in the textbook of ours or the other textbook that you may find to share with your classmates. Okay, so, okay, 4 and 5. Anyway, I think that's the end of section 4.3. The next one is a recursive algorithm. Here, and factorials. Computing n factorials. Yeah, you have seen n factorials. Okay, let's compute those. Yeah, this pseudocode gives you the output as n factorials, and this is the code that I made. So you can test it. In here, factorial is emphasize. If you multiply the first one and the next integer, and then make that as a factorial, then multiply the next number to find the output, and replace it as a factorial, then multiply the next number to find the factorial of the next numbers. And that algorithms will give you 10 factorials like this, and 50. So like 5 factorial, this 6 factorial, multiply 6 on that, 7, 8, like this. And if you have a 20 factorial, as you see, the 75, the factorial really increase very fast. So factorial is the ones that you have to worry. Factorial is too big when n grows. Okay, algorithm 4.2 returns the value of n factorial. Okay, we can prove by mass induction that that n factorial that the algorithm works. And also, the next example, 4.5 is another interesting example. A robot can take of 1 meter or 2 meter, and we write an algorithm to calculate the number of ways the robot can walk n meters. Okay, find the number of ways that a robot can reach n meter if the robot can only moves 1 meter or 2 meter at a time. Okay, for example, if distance is 1, then there's only one way. The robot can go there by one step. If distance is 2 meter, then robot can go there by 1 meter and 1 meter. That's one way. Or he can go 2 meter by just one step of 2 meters. So there are two ways. But if it's a 3, then there are more ways. If it's a 4 meters, then there are more ways. Then what's the kind of rule to find the general formula to find the number of cases? Idea is this. Yeah. Work of 1 is 1 and work of 2 is 2. We define in these functions. Then robot, when n is bigger than 2, then robot begins by taking a step of 1 meter or a step of 2 meters. A robot begins by taking 1 meter step, then a distance of n minus 1 meters remains. Okay, so yeah, we can use recursive ideas. Okay. If robot, the remainder work can be completed by work of n minus 1 ways. Okay. The robot begins by taking 2 meter step, then a distance of n minus 2 meters remains. Okay, so we can use the number of ways to reach n minus 2 meters by robot work. So the work must begin with either 1 meter or 2 meter step. So all the ways to work n meters are accounted for with this. That's it. That's it. That's the recursive relations. With this simple formula, yeah, we can find the number of ways to reach n meter by the robot. So our recursive algorithm to compute work of n is sum of work of n minus 1 plus work of n minus 2. That's it. So, and when n is equal to 1 meter, there's one way. When n is equal to 2 meter, there's 2 ways. So base cases are 1 and 2. So this is a robot work, recursive algorithm for the given robot work. So that can be coded in this way. So you can find the robot work. What's missing? Robot working in rect else. Copy. That's missing. Definition, define it, and work 0 for 1, 1 for 1. And it's 102, print. Line 4, 1, 2, 3, 4. Anyway, expected intent. W, you are, this is, yeah, this shouldn't be here. Yeah, when we, yeah, you can fix it, yeah. The robot work, W was defined properly. So N of 1, W of 1, W of 0. Okay, yeah, you can check it. Anyway, but this sequence work of this sequence, which starts from 1, 2, 3, 5, 8, 13. You will see the relations. The next term comes from the addition of first two numbers. 1 plus 2 makes 3, 2 plus 3 makes 5, 5 times plus 8 makes 13, like this. So the next term is the addition of the earlier two terms, which is very closely related to the Fibonacci sequence. Fibonacci sequence is defined in this way. F1 is 1, F2 is 1, and this is a recursive relation. So two earlier terms. So 1, 1, 2, 3, 5, 6, this is it, which is very similar to the robot work, except the first two terms are 1 and 1. Okay. Okay, so from here, yeah, we will see, you will see the relationship between the robot work and Fibonacci sequence. And let's check. I think yeah, this should work. Yeah. I missed something else. Yeah, we were missing this part before. Here, this is a Fibonacci sequence. This is a fourth term of Fibonacci sequence is 3, and 56th term is this. 125th term is like this. So Fibonacci sequence can be counted here. So I think, yeah, we were missing this. print and returns. I'll fix it. Anyway. Okay, so last example of chapter 4. We use mathematical induction to show that Fibonacci sequence satisfies these relations. How do we show this? When we want to show some terms is the equality for the integer numbers, for all integer numbers, for all positive integers, and we can use the mass induction. So we want to show this by mass induction. So first basic step, and we show it is true for n is equal to 1 first. We just substitute n is equal to 1 to have this, which is clearly true because we know F1 and F2, which is 1, F3 and 4. And so we can easily check this is true. And next, we assume this is true for n, so we assume that's true. Then we show this is true for n plus 1 as well. So we start with fn plus 3 square minus f of n plus 2 square, and we expand it and use this to have the right-hand side is fn plus 1 times fn plus 4. Then it's been proved. So by mass induction, we could show this equality is true when we have a Fibonacci sequence that starts from 1 and 1. I think that's the end of chapter 4. And here is the exercise, and here is the problems, yeah, even I gave you the presentation of those, explanation of those solutions. And yeah, I gave you the page, the exercises in page 211 to 213, which is a self-test problems of 16 and computer exercise of this. Yeah, you don't have to solve all the problems, but try to solve for 4 or 5 problems and to share. And also, I have added some informations in Q&A, and it was very interesting to find these ideas, teaching discrete math via primary historical source that you can find in these web addresses. Here, it shows striving the efficiency in algorithm and discover Huffman code and networking and spanning trees and project on programming correctness. And these, if you go this web address, and you will find some of the project which was done by the other undergraduate students in the United States, which this project was supported by National Science Foundation, and which can be shared with you. And it was interesting. So you may take a look on this. Algorithm, recursion, and induction, Euclid and Fibonacci. And yeah, this will be interesting. Yeah. And this shows how those ideas originally started, how those persons who started to think that subject in the way that we are using now, with the historical sources of the first papers and articles and books. I think that's the end of chapter 4. Any questions? Okay, then summarize what you have learned today and start.